So now we're going to go on to a specific acceleration, which is known as gravitational acceleration. So gravity is a force which causes objects to move closer to the Earth's core. So if you ever threw something up in the air, so I'm throwing my pen up, it will always come down at the same acceleration as any other object. So gravitational acceleration itself is independent of mass. In these problems, we're going to assume we're in a complete vacuum, so we won't have any drag forces acting on us, and everything moves at the same constant downwards acceleration, which we label as little g. There's a reason I call it little g, is because later we're going to meet big G in astrophysics, which is Newton's constant of universal gravitation. That's a bit of a mouthful. But this value for G, little g, is 9.8 meters per second squared. Now, there are a couple of assumptions that we have to go off of and little tidbits on gravity. So, gravity as a vector will naturally always point downwards when an object is in motion. The nature of gravity can change the mathematical approach for it. So, no matter if an object is moving up or down in a gravitational field, the gravitational vector will always act downwards. We will note this as mg when we get to forces, but for now we can just discount the mass and just have the acceleration vector downwards as g. Depending on if the object is going up or down, the value and signage for g will be different. So when it's slowing an object down, it will naturally be decelerating, so that's minus g meters per second squared. And if gravity is helping an object speed up, it will be positive g meters per second squared. So it relies on the exact same logic from CVAT, though a lot of people seem to be a bit confused as to why we use positive and negative g at some points. You can, in some cases, have it as the magnitude of g to govern all cases, but I really wouldn't recommend it because the maths with moduli can get a bit crazy at times. So I would just recommend knowing when to use positive and negative g. A modeling assumption as well that we're going to use is that gravity is not actually the same all over the Earth. If you've looked up videos of people pouring water off the Hoover Dam, the gravity is actually slightly stranger there because of because of a lot of things. As well as that, there are places on Earth where gravity appears inverted, and especially even at the North Pole, the gravitational acceleration is slightly weaker than, say, around the equator. So, as I said in this little paragraph here. In practice, the difference is entirely negligible. The difference is only about 0.01 meters per second squared throughout different places. So with the use of our significant figures, that difference is just entirely forgotten about, and we always use g as 9.8.